Okay, guys, in this question, we are going to compute the flux of a vector field, which is just x, I, y, j, z, k. Now, the surface here is what is called a paraboloid. So this is z equals 25 minus x squared minus y squared. So why is it called paraboloid? If you just remove y squared, you will get just 25 minus x squared. And that is a parabola, right? So this is an extension to a 3D parabola. That's why it's called paraboloid. Now, I also wanted to show you what it looks like so you can see. This is the paraboloid right there, and it's actually goes all the way down forever, but it is cut because it has to be above the xy plane. So the projection of this paraboloid, as you can see, is a circle of radius 5. Okay, so this is what is the projection of the surfaces. Just imagine that each coordinate, each of every point on that paraboloid, you switch it to from xyz to xy0. So it's just gonna drop to it this circle, right? So the circle is going to be the projection on the xy plane. All right, so let's see if we can compute this integral. Now, what actually happens here, this flux thing, where does this come from and how do we compute it? So there is a formula that you can use for the flux, but I want you to understand a little bit out of it, like what is this n? So it turns out that n is actually a vector normal to the surface, and it should be a unit normal. So the surface is represented by z equals g of xy. Okay, so this is some surface z equals g of xy. So what I could do is move this g of xy to the other side, so I will get negative g of xy plus z equals 0. And so it turns out that to find the normal vector to the surface, it can be shown that that normal vector is going to be the gradient of the side. Okay, so the normal vector, we'll just call it capital N, is the gradient of the left-hand side. But what is the gradient? So let's take a look at the derivatives. The partial derivative with respect to x will become negative gx, right? Because z doesn't have an x, so that term will just go to 0. Now, the partial derivative with respect to y will be negative g with respect to y, and again, z will drop out. And then when you differentiate with respect to z, when you do the gradient, right, the first part will drop out because it doesn't have a z, and the second part will become 1. So that would be the normal vector. But in the formula, actually, you have this unit normal. What does that mean? It means the vector that has the same direction as this capital N, but it has unit length. So you have to divide it by the magnitude of this gradient, okay? And what is the magnitude of the gradient? So we'll take this vector and we'll what we call normalizing by dividing by its length, you make it a unit vector, length 1. So what happens? Well, negative gx is just going to be gx squared, right? Because negative is going to go away. And then this is going to be gy squared, and then this is going to be 1. So that's your normal vector. But remember when we were switching to regular dA integral over the projection, what would happen? So we would take f dot with this n, so that would be negative gx, negative gy1, and then we divide by the square root. But remember that the ds part, if you remember, when you switch to from surface integrals to double integrals, you have to multiply by that root. So ds is not just dA, it's the root gx squared plus gy squared plus 1 and then dA. And look what happens. This whole square root is just going to cancel out. So this is how we compute flux. So there is a formula to compute flux. And that is take the force dotted with the vector negative gx, negative gy1. And this is now going to be a regular double integral over the projection of the surface onto the xy plane. This is why the formula. Okay, so I didn't want to just give you the formula for the flux without explaining where it comes from. Anyway, let's now turn to the actual question. So here we have z equals 25 minus x squared minus y squared, and this part right here, that's your g of xy. Okay, so let's compute gx. So that's the partial with respect to x. Well, 25 turns into 0. Then it's going to be minus. X squared turns into 2x. Y squared will just become 0. And then gy will be similarly just negative 2y. Okay, so now let's go ahead and compute the force. Well, what is our force? X, Y, Z, right? Because it's Xi plus Yj plus Zk. And then we find the dot product of it with negative Gx. Well, negative of a negative is a positive. Negative Gy will be 2y and 1. Now, hopefully you remember how to compute a dot product. So what it is we take each component, multiply by the other component, right? So multiply this one by the corresponding y component and this one by the z, and then we add them up, and it's not a vector. Dot product is a number, or in this case, it's a scalar field because it has x and y. So this is 2x squared plus 2y squared plus z. And that's what we would be integrating, except anytime you are integrating surface integrals, you cannot leave z in there because it's supposed to only have x and y. Now, what is z on the surface? Because remember, you have to be on the surface. It's a surface integral. Z on the surface is 25 minus x squared minus y squared. So we have to further substitute everywhere where we see z, we plug what it is. And then when we simplify this, this is going to become 25 plus x squared plus y squared. So that's what we need to integrate over the projection of this surface onto the xy plane. But I already showed you that the projection, remember the projection when I showed you the picture, is that circle of radius 5. So we are going to switch it to polar, because anytime we are integrating over a circle, it is much easier to integrate by switching to polar coordinates. So how do we do that? Well, we need to remember that for polar coordinates, x squared plus y squared becomes r squared. So we are actually integrating 25 plus r squared. Also, when you switch to polar coordinates, you need to multiply everything by a special, what we call Jacobian, which comes out of switching from rectangular to polar coordinates, and this is an extra r. Remember, the pirate says r, so don't forget to add an extra r, rather multiply by an extra r when you switch to polar. So this is dr d theta, and we set it up over the circle. So 0 to 2 pi for theta and 0 to 5 for r. Okay, now this integral is splittable, so we're going to split the theta separately. There is no theta there. Multiplied by the r, so let's go ahead and distribute this. So this is going to become 25r plus r cubed dr. Okay, so the first integral obviously will just be 2 pi. The second integral is going to be 25. Now r to the power 1 is going to be 1/2 r squared, plus r to the power 3 is going to be 1/4 r to the 4th. And we substitute 0.5. So at this point, we are just going to go into the Desmos calculator and see if we can compute the expression in parentheses. Obviously, when you substitute 0, you will get 0. So 25 halves multiplied by 25 plus 1/4 multiplied by 5 to the 4th. Okay, so it's going to be some kind of ugly fraction. So it's going to be 2 pi multiplied by 1875 over 4. And we can actually cancel that 2, so we will get 1875 pi divided by 2. Pretty easy, pretty easy. Okay, so this is going to be 1875 pi over 2. Here we got 25r plus r cubed. Oops. We got 0 to 2 pi. We got 0 to 5. And that's what we got.